teacher went to a tournament and he asked me to give you a class name. And he had me give you a quick review of what we've seen so far. First, we're going to see law of sines. Remember that the law of sines is applied in any oblique triangle whenever we want to get sides or angles. The equation for law of sines was sine of A over side A equals sine of B over side B. That is equal again to sine of C over side C. As we can see, the little letters represent the sides and the big ones represent the angles. We have two cases in which we can apply the law of sines. First of all, when we have two angles and one opposite side, and the second, when we have two sides and one opposite angle. This is because if we were to have an opposite side and an opposite angle, then this equation wouldn't apply. Edu, wake up!
Huh? What happened? Hi, teacher, sorry. Hi. Wait. Alright guys, now we're going to see law of cosines. Well, the formula for law of cosines is this one, where the little letters represent the sides and the big letters represent the angles, which is a squared equals b squared plus c squared minus 2bc times cosine of the angle of A. Okay, well, this can be used in two cases. When you have one angle and two adjacent sides, or when you have three sides, and this to obtain the rest of the angles that are needed. And the applications for this are the vector quantities, such as aircraft navigation, which is everything that has to do with the airplanes. For example, the time they need to start going down before landing into an airport, they have to calculate all that with these calculations.
The inverse trigonometric functions are the inverse functions of the trigonometric functions. But in order to become an inverse function, the domain of that trigonometric functions needs to be restricted, so it can become a one-to-one function. So, as a result of the domain being restricted on the original function, on the inverse function, this restriction is reflected on the range, as it can be shown on the screen. For time reasons, we are not going to explain each of the range and domain of the functions, but you can pause the video and see them all. Also, we are going to present the graphs right now. A sinusoidal curve is a mathematical curve that describes a smooth repetitive oscillation.
Well, for the basic trigonometric functions, we will always have a general formula, which is the basic one when there are no changes, but those characteristics might change. For example, the amplitude, which is half the distance between the lowest point and the highest point. So logically, we understand that the bigger the amplitude is, it's because the graph is bigger. Then we have the period, which is the horizontal distance traversed before the y-axis repeats. So the bigger that is the period, it will be larger. Then the frequency, which is the number of complete waves that we have in a transverse distance of 2 pi. So for example, if we have if the complete wave is 2 pi, then our frequency will be 1. If our complete wave is pi, then our frequency will be 2. The complete wave is represented in k, so the frequency equals 2 pi divided by k. Then the angular frequency in a scalar measure of rotation rate, it gives you the frequency with the phase changes. And then we have the phase shift, which is the units the graph is shifted horizontally. It can be to the left or to the right.
Simple harmonic motion is a very important way of oscillation. It is given whenever an object is moving towards its equilibrium point based on restoring forces. Two of the most common examples of SHM are mass spring oscillator and the pendulum. Given the equation for SHM, it is easy to identify the position of an object at any given time and determine whether if it is at its maximum or its minimum. This is due to the fact that they are sinusoidal that equals the single resonant frequency. We know that whenever the object is at its maximum displacement, the velocity is going to be zero, since the velocity is constantly changing. And when the displacement is equal to zero, then our velocity is going to be equal to its maximum point. This is due to the fact that when the displacement is at 0 point, there is no force applying to it. The frequency depends on the restoring force, and for a mass on a spring, the restoring force is based on the equation F equals minus K plus times X. The finalization equation contains a complete description of motion and other components which can be obtained for it. This is equal to y equals a sine of omega times t equals to the sine a sine of the square root of k over m times t, in which the velocity and acceleration are given by omega a cosine of omega times t, in which a is equal to minus omega 2 squared times a times sine of omega times t, which is equal finally to minus omega squared times y. Omega represents the frequency which is related to the frequency of the motion and is inversely related to the period, given the equation, the previous equation. Finally, the total energy of our undamped oscillator is the sum of kinetic energy and potential energy. The total energy is a constant and is equal to a kinetic energy plus potential energy. So it's equal at E equals kinetic energy plus potential energy, which is equal to 1/2 times K times A squared. And this is what we call a simple harmonic motion. Basically, the sinusoidal that we get equals a single resonant frequency which we can insert in strings or in, like I said before, pendulums.
Well, the steps needed to make this project were, first of all, understand. We get together, all the three of us in the library, and we first of all we read the rubric. Also, we read the instructions of the project to see what were the topics that will be covered during the realization of this project, and we according to what they asked for, we'll look in our notes to see what we already have seen to understand a bit of the topic. Then we investigate. In teams, we divided equally all the part of the theory to give us a clear idea, and we answered everything that each of us knew. Then, in order to complete the theory, we searched for resources, the formulas, and the procedures that we didn't have very clear, and we answered well all the questions that were asked. And then, with all the theory completed, we were able to know what was fully the topic about, and then we we were able to look for the applications, because I think that the important part of the project it's not to know like the formula, the graph, or to know the changes on the graph, but to know why is this important, what is it used for, and why we are seeing it in class, why do we need it for life. So well, we look for the daily life uses, as we saw, as we already that we're going to explain on the project further in the project. Then we solve the problems. With all the information gathered before, we were able to solve the problems and complete all the aspects that were asked. And finally, we made the relationship between the projects and the applications, which while the problems has to do with our daily life. Oh my god, I can't believe I slept the whole class. You know what? I don't even care anymore. Let's go to the movies.
Yeah, but wait, where are we going to see it?
Oh, I don't know. We should check it on the internet, like where to sit at the movies.
Oh, yeah, we should do that.
Okay, take your phone out because on my iPhone 4. Okay, let's do it on my iPhone 4.
Everyone knows that the apparent size of an object depends on its distance from the viewer. The farther away an object, the smaller its apparent size. The apparent size is determined by the angle the object subtends at the eye of the viewer. Imagine, if you are looking at a painting hanging on a wall, how far away should you stand to get the maximum view? If the painting is hung above eye level, then the following figures show that the angle subtended at the eye is small if you are too close or too far away. The same situation occurs when choosing where to sit in a movie theater. So, through this project, it is going to be answered two problems about where to sit at the movies. On the first one, it is going to be included a height variable, while on the first one, there is not going to be a height variable. So let's go. On the first problem, as it is shown on the diagram, it is asking to us where to sit on the rows and get the maximum value of theta with these variables. The first one is that the first row of seats is 7 feet apart from the screen. The screen measures are of 22 feet. It is 10 feet above the ground, and that the point of view is 4 feet above the ground. And the problem asks us to demonstrate this formula, also this subtraction formula, and finally to graph the function. Well, here's the diagram of the problem in which the angle theta is a result of the subtraction of angle alpha and beta. So, answering the first demonstration, let theta be the angle that stands for the vision angle of the viewer. This angle can be expressed in the terms of alpha and beta as alpha minus beta. And alpha and beta are functions of x defined by the inverse function of tangent of 28 over x, and beta is equal to arctangent of 6 over x. So, substituting those two formulas, then we obtain the first demonstration, which is theta is equal to the inverse function of tangent of 28 over x minus the inverse function of tangent of 6 over x. Then, answering the second problem, which is the second demonstration, then we obtain that as theta is equal to the difference of two angles, if we apply the identity of tangent a minus b equal to tangent of a minus tangent of b over 1 plus tangent of a times tangent of b. Then, after we apply the identity on this function, we obtain all this, which, when we clear theta, we obtain that theta is equal to the inverse function of tangent of 22x over x squared plus 168, which is what the demonstration asks us to obtain. Now, in order to calculate precisely where to sit at the cinema, we need to do the following procedure. In the last expression, we observed that theta depends directly on the value of x. So now we want to determine the trail of x as well as that one of theta. The trail of x is a set of discrete values of 7, 10, 13, 16, 19. This is because the distance between each row is of 3 feet, so it goes increasing by 3 feet each time. But then the trail of tangent of theta can be obtained from this equation over here, which is the last one that we mentioned, and we pour out the x terms of tangent of theta. After we pour them out, we obtain a second degree equation, which we write over here, and then as the determinant, which is the value inside the square root, cannot be negative, we can determine a set of values in which tangent can be found, which are these ones. And after we clear tangent of theta, we obtain that tangent of theta has to be equal or smaller than the square root of 484 over 672. In other words, the highest value that tangent of theta can get is, well, surprise, a square root of 484 over 672. Now, taking into consideration that the lowest value that x can take is 7, the trail of tangent will be 22 times 7 over 7 squared plus 168, and the highest value that it can get is a square root of 484 over 672. So, transcribe that trail of theta will be of 35.36 degrees, included, to 40.32 degrees, also included. So, in order to determine the value of x, where tangent of theta can take its highest value, it will be enough to substitute the highest value, which I already mentioned quite enough times, in the equation before, and we obtain that the highest value is 12.96, which is really close to 13 feet. In conclusion, the maximum tangent of the angle that subtends the screen at the eye of the viewer, theta, presents when it is at a distance of 13 feet from the screen, or in other words, on the third row. So 40.32 degrees is the highest value of the angle that can be subtended from the screen to the eye of the viewer, and this is when he is at the third row. Here is the graph that explains it, and in effect, it shows that at 13 feet, or close to it, it is its highest value with 40.32 degrees. Now, for the second problem of where to sit at the movies, we now suppose that starting with the first row of seats, the floor of the seating area is inclined at an angle of alpha equals to 25 degrees above the horizontal, and the distance that you sit up the incline is x, as shown in the figure. So, in this new problem, we are asked to know theta again, but with a new variable, which is the inclination that each seat has. Well, here's the diagram of the second problem, and in order to do the first demonstration, then we start with the problem. Let theta be the angle at the screen subtends in the eye of the viewer. This angle can be expressed in the terms of the side of A and B by using the law of cosines by theta equals to the inverse cosine of A squared plus B squared minus 484 over 2AB. So we see that over here and over here are sides A and B, and this is obtained from the cosine law just by clearing the angle of theta. Now, from figure 2, which is this one, we know that A squared is equal to 7 plus x cosine of alpha squared plus 32 minus 4 minus x sin of alpha to square. We simplify it, and then we obtain Oh, hold on. And we also obtained that b is equal to set to all that, that b squared is equal to all that, and being alpha equal to 25 degrees, we have that sine of 25 degrees equals to 0.444226, and cosine of 25 is equal to, well, it approximates to 0.9063. Now, by substituting a and b in the first equation that we obtained, which is this one, we obtain this a hell of a big equation, which just by simplifying, we can obtain that the demonstration that the problem asks us. Well, it seems like a complete loss of time, but it was really effective. Then here is the graph. The graph of equation 2 is the following one, and it shows us that estimated value of x that maximizes theta is of 9 feet. So the spectator should be seated on the fourth row, and the maximum angle that subtends the screen to the spectator's viewer will be alpha equals to 49.7 degrees. And here is the graph that proves our knowledge, saying that at 9.29 feet, the angle will be at its maximum with 49.7 degrees. Finally, but not least, the problem 7 of page 231, it is stated that when two species interact in a predator-prey relationship, the population of both species tend to vary in a sinusoidal fashion. So, in a certain Midwestern country, the main food source of barn owls consists of field mice and other small mammals. The table gives the population of barn owls in this country every 1st of July over a 12-year period. So, the data that the problem gave us was this one, which states the population of owls at each year. Then, here's the scatter plot with all the dispersion points. Then, here is the function that the student discovered just by applying transformations to that scatter plot of before, and the equation that the student discovered was this one. F of x equals to 30 cosine of p6 times x minus 3, and all that plus 50. Then we use Minitab to discover the real, or well, the most precise regression model, which in this case was 25.7513 times cosine of 0.524739 times year, which is x, minus 3.028028, and all that plus 50.5617. I think it was pretty close, but not close enough as this one of the problem.
Another application for sinusoidal curves in real life we can observe is in the amount of hours of daylight throughout the year. This is because they have a periodic form. Due to the fact that the Earth moves around the sun throughout the seasons, the amount of daylight is going to change throughout the year. And whenever we do a scatter plot of this example, we can see that it forms a sinusoidal curve through all the seasons of the year. This example also happens with temperature. When we do a scatter plot, we can observe the formation of different sinusoidal curves. These are called sinusoidal regression models.
I have seen this topic before at school, and it wasn't until the end of the project that I realized that this topic has a lot of uses. For example, in architecture, it can be useful to do measures or everything that is needed in order to get the measure or an angle, like in construction, airplanes, or edification. Also, I learned the real meaning of the sinusoidal function and the reason why the graphs are the way they are.
Thanks to this project, I was able to recognize, apply, and visualize trigonometric functions and ratios almost everywhere. Turns out that these simple ratios that we observe in math, like triangles, have much more useful applications in life, like in architectonic fields. I find very interesting that when you graph them, they form sinusoidal curves, and that they are strictly related to the unit circle, and I find their properties very interesting. How we restrict things in order so they look a certain way, I find it quite remarkable. And actually, one of the most interesting parts of the project for me was simple harmonic motion. I think it's simply outstanding how easily we can connect the dots for saying. I don't think I would have been able to make that relation myself, but I find it a very, very interesting and useful. And if it weren't for this project, I wouldn't have achieved that sense of recognition and of logical thinking as I think I have now. Thank you.
In conclusion, it can be said that even though sinusoidal curves seem irrelevant to real life, they are actually used in it when describing continuous cycles. For example, in the population of a certain animal in ecosystem. Also, it is concluded that the basic trigonometric ratios and principles are really important in physics and in other branches of science, as they help to establish parameters for the motion and velocity of an object. In my personal opinion, this project helped me to understand how different concepts or topics can be related through trigonometry. Team conclusion. In conclusion, we learned that we work better in team than just alone. Also, we affirm our knowledge in love cosines and sines by discovering the uses that they have in real life. Finally, the sinusoidal parameters help us to understand how they can be modified in order to fit a set of data. At last, we learned how to use the basic trigonometric ratios, principles, and identities in order to arrive to the formula or equation of a certain problem or situation and create our own conclusions about the problem, only by using what we know.